Time to do some calculus. Derivatives of trig functions. Going to do 1 through 25 odd here. Once you know what the derivatives of the trig functions are, I think these are pretty easy. I'm going to combine them with our other rules we know so far. That'd be the power rule, the product rule, and the quotient rule. Those are our 3 rules. And I guess you could think of these as rules if you want. So if you've got f of x, and you're trying to find f prime of x, if f of x is the sine function, the derivative is cosine. If at the cosine function, then the derivative is negative sine. Definitely see those the most often. And what else? Derivative of tangent is secant squared x, and then the derivative of cotangent x is negative cosecant squared x, and derivative of secant x is secant x tangent x, and the derivative of cosecant x is negative cosecant x cotangent x. I think I mentioned in the notes there's some patterns here for you to latch onto. It's not like you have to memorize 6 completely unrelated things. Derivatives of all the co-functions are negative. And you can see like secant, secant tangent, cosecant, cosecant cotangent. So lots of good stuff there going on. All right, let's jump into it. So number 1, the derivative of this is going to be 4. Derivative of cosine is negative sine plus 2 cosine x. For number 3, f prime of x. Looks like I got some product rule here. I'm going to treat negative 4x squared like it's the first and cosine x like it's the second. So the derivative of the first is negative 8x times the second plus the derivative of, plus the first, sorry, times the derivative of the second. And there's 2 minus signs that cancel out to be a plus, but you know, we're all adults here. You can rewrite that or not. Number 5, looks like I got some quotient rule. That's going to be, let's see, low, d high, the derivative of the 5 is 0, the derivative of minus cosine is positive sine. It's low d high minus high d low. Sure, there's some stuff that's going to simplify there. It looks like we might have a sine squared plus cosine squared. So, sure, yeah, you could simplify that. Trig. But that's where it starts. And I'll leave it to you. See if you can get it to match up to the back of the book. Number 7, f prime of x is equal to derivative of secant, secant x tangent x, minus the square root of 2 times the derivative of tangent x, secant squared x. Number 9, you know the Beatles song? Let's see, 4 cosecant. So 4, the derivative of cosecant is negative cosecant x cotangent x, minus cotangent, the derivative of cotangent is minus, which is going to turn that into a plus, cosecant squared. Number 11, the derivative of secant x tangent x. I'm going to have to do the product rule there. Derivative of the first times the second plus the first times the derivative of the second. And maybe just take a quick second here to make sure we understand notation, what these things mean. So there's 2 tangents here, so you could write that as like tangent, like the whole thing squared, but that's what this notation means. Tangent x times tangent x is tangent squared of x. So when we see one of those, doesn't matter which trig function, of course, that means this. That's what that notation means. And of course, that's important in a situation where you have to evaluate it, even if you have your calculator handy and you're allowed to use it. Oops, didn't mean to put that parentheses there. So I could do secant cubed x and just ignore that. Right? In your calculator, you'd have to enter it like this. Your calculator doesn't speak that notation. Number 13, looks like I got some quotient rule. Right, low, d high, minus high, d low, some negative signs could be cleaned up there, and low low. All right. This is kind of a funny one. You could go through the process and be like, okay, got to do my, you have to do product rule here because you don't know how to do the derivative of a function squared. That's actually going to be covered in the next section. But what we are hoping, all of us who care about mathematics, is that you recognize, oh, sine squared plus cosine squared of x, that's just 1, and of course the derivative of that is 0. You could do it, if you didn't realize that, you'd have to recognize that sine squared x really means this. And then do the product rule on that. So the derivative of the first times the second plus, still on this, the first, well, it's the same thing, so there's going to be 2 of those, right? Plus, then I've got the derivative of the first times the second, and then the other one, when I switch them around, that's going to be 2 of those, and you can see that's the same thing, so that's 0. So you should still get 0, of course, because that's the right answer. But recognizing that identity is definitely the way to go. In 17, there's a little bit of a benefit here if you recognize that sine x on the top of our f of x, we have sine x times secant x, but secant is 1 over cosine x, and that's equal to tangent x, and that's going to save us some trouble. So the top of this, instead of being sine x secant x, is just tangent x. So when I do my quotient rule, it makes things a little easier. So I've got low plus x tangent x. D high now is just secant squared x. You should get something equivalent to this if you don't simplify, but it's going to be more work. Minus, low d high minus high d low. So the d low, the derivative of 1 is 0, and then I got to do product rule on the x tangent x. So the derivative of the first is 1 times the second plus the first times the derivative of the second. That's what that looks like over low, low. Want to simplify that? Great. I don't, not really. It does look like that there's going to be some like term action here, that there might be something that cancels out this x tangent x secant squared x, and then a minus x tangent x secant squared x. So there is some simplifying that could happen there. It's a fun game that you should play every once in a while, not in every problem, but every once in a while you should say, you know what, I am going to get my answer to match up to what they have in the back of the book. If it's the last thing I do. So for these, we want to find the second derivative. So let's see. dy dx is a little product rule here. Derivative of the first times the second plus the first times the derivative of the second. And then when I find the second derivative, derivative of that is just minus sine x. The derivative of this, let's see, I'm just going to treat it, since I have that bracketed off, I'm going to treat this like it's the first and this like it's the second. So the derivative of the first times the second plus the first times the derivative of the second. And so there's minus 2 sine x there, minus x cosine x. You could simplify that a wee bit. Number 21. Alright, y equals x sine x minus 3 cosine x. So the derivative is product rule. Derivative of the first is 1 times the second plus the first times the derivative of the second, minus 3, derivative of cosine x is minus sine x. And then those could be put together, 4 sine x's. And what I think I need to do that here, or I want to do that, because I'm taking another derivative. So if there's more work to do, then I think that there is definitely a payoff for simplifying. Okay, so now I've got derivative of 4 sine x is 4 cosine x plus product rule, derivative of the first times the second plus the first times the derivative of the second, x. Let's see, I don't know why I put that in parentheses, x times minus sine x. Right, so 5 cosine x minus x sine x. And 23, another second derivative. I'm going to give you two options here. There's a trig identity. Let's do it this way first, then I'll remind you of another thing you could do. So product rule here, derivative of the first times the second minus the first, plus the first times the derivative of the second, which is going to be that. Now to find the derivative of this, I have to treat these like product rules, because I don't know how to do composite function derivatives yet. So that's cosine cosine. So the derivative of the first would be negative sine times the second, which is cosine x, and then that's going to happen twice because the first and the second are the same, so I'll squeeze a 2 in there. And then here I have minus, and then sine x times sine x. The derivative of the first is cosine x times the second, and they're both going to be the same. So I end up with, looks like 4 of those, minus 4 sine x cosine x. All right, now here's the thing. You could, if you remember this trig identity, that the sine of the sine of 2x, the sine double angle identity, is this. You know, you did a bunch of stuff with trig identities last year. I know. It probably wasn't your favorite thing. I don't know. Do we use them in calculus? Yeah, sometimes. You better know that sine squared plus cosine squared is 1, for sure. Of all the other, Pythagorean identities, like the variations of that, when you divide by sine squared or cosine squared, the ones with secant and tangent and cotangent and cosecant. You need to know those 3. If there's any other one trig identity that comes up, like kinda, sorta often, it's probably this one. So that's a good one to know. The half angle ones, and I don't think you're going to see those much, or at all. So here, this one, if we recognize, oh, I got a sine x cosine x here, so if I divided both sides of this by 2, then this is the same as 1/2, I'm just looking at this identity, moving the 2 over here, 1/2 sine 2x. Oh, and you know what? I guess we can't do it that way right now because this is a composite function. I got a 2x in there. So never mind. If you already knew this stuff from section 3.6, then this would make it easier to do. But for right now, that makes it impossible for us to do because I only know how to do derivatives of sine of like regular x in there. I don't know how to do composite functions. So anyway, good to know that. That'll come in handy maybe soon, like in 3.6. So last one, number 25. Equations of tangent lines, that's a thing that's not going away. I'm starting to pick up on that theme. The graph of y equals tangent x. So what's the derivative? Y prime is equal to the secant squared of x, which for the purposes of actually doing it without a calculator, which is the idea here, that's 1 over the cosine of x squared. Like, that's what that means. This is a nice way to write it. But if I'm actually going to think about it and try to do this, then probably I'm going to be thinking that. And this is like sine over cosine, if you like. So for A, B, and C, I have, to write the equation for a line in point-slope form, I need a point, and I need slope. So these are the x-coordinates that they're giving me. Let's see, what's the y-coordinate here? To find the y-coordinate, well, you just do what you've always done, plug the x-coordinate into the original function. That's 0, tangent of 0 is 0, tangent of pi over 4 is 1, tangent of negative pi over 4 is negative 1. Right, those are things we should know or be able to easily reconstruct from a mental picture of the unit circle. Well, I mean, if you needed to draw one, I guess you could, but that's going to slow you down in the long run if you have to do that every time. Now I need to find the slope, so that's y prime of 0, y prime of pi over 4, and y prime of negative pi over 4. Okay, so how am I going to approach this? I'm going to go ahead and find the cosine value and then square it and then flip it over. So the cosine of 0 is 1, and 1 squared is 1, and when you flip that over, it's still 1. So what line is this that goes through the origin and has a slope of 1? It's just the identity. You know that this line is sometimes called the identity because whatever you put in, you get the same thing out. All right, so pi over 4, what's the cosine of pi over 4? The cosine of pi over 4 is the square root of 2 over 2. If you square that, you get 2 over 4, or 1/2, and if you flip that over, you get 2. So I have a line that goes through this point, has a slope of 2. So let's see, that's going to be y minus 1 is equal to 2 times x minus pi over 4. And just to re-emphasize here, the reason we like point-slope form is because it has the right information coded in it. If I looked at this, I'm like, okay, whoever wrote the equation for this line, the point pi over 4 comma 1 is important to them. The y-intercept, not so important. This point is important. That's our point of tangency, and it has a slope of 2. So here, let's see, what's the cosine of negative pi over 4? That's also the square root of 2 over 2 squared, and we'll flip that over so it's the same slope. If you picture the graph of the tangent function, it might be, I don't know, slightly instructive, intuition building, to think about these 3 points, where they are on the graph and what these slopes are, how that makes sense. So at the origin, we got a slope of 1, and then at pi over 4 and negative pi over 4, we have a slope of 2. So that all looks groovy there. You can't see the very edge of that, can you? There you have it.